Right, so hello everyone. I'll be talking about Cooler, Bigger, Warmer, Smaller, which is a story about spatially explicit species and size stratification and behaviorally thermoregulating salmonids. This is a project taken on by myself and Anton O'Sullivan. So to begin, I'll go through an overview of my presentation. I'll start by giving some context as to how I began this study. I'll talk about the methods that were used and the analyses conducted. And then I'll go into some specific observations that we saw throughout the study and conclude with some closing points. So for context, last summer, I was unfortunately Anton's summer student, and we essentially just worked in remote sensing on the Cairns River and the Little Southwest Miramichi River, where we had been placing underwater cameras at cold water refuges. Our regular work duties were naturally to basically just change out the batteries and the data on those cameras. And so for the study itself, we had a very opportunistic field visit where one day we showed up to switch out the cameras and had seen something very, very neat. So I'll start by talking about behavioral thermoregulation. So it is a behavioral response incited by ectothermic organisms. So an ectotherm is an organism that needs to regulate its internal body temperature with the environment, with the help of the environment. So an example would be like a lizard laying in the sun in the desert to warm up its blood. And then on the other side of ectotherms, we've got the poikilotherms, whose body temperature is a little bit warmer than the environment, if not close to it. And poikilotherms are, or I guess salmonids are poikilotherms. And so when water temperatures reach uncomfortably warm temperatures for salmonids, they will seek cold water refuges to cool down their internal body temperature. So that is the heat and stress response in salmonids. And this is a picture from one of Anton's papers in preparation of a thermal aggregation of adult Atlantic salmon for an overview of what a thermal aggregation looks like. The contemporary importance of this, obviously, as we all know, the climate is changing. And so these events are becoming increasingly prevalent and relevant to us to study in order to ensure salmonid survival, because at extreme temperatures, they will die due to warm waters. So before I got into this study too much, I was given a couple of papers to read. The first one by Bro et al., where 2+ juvenile Atlantic salmon were seen to occupy the coldest parts of the thermal refuge. That's important in behavioral thermoregulation. We see the oldest/largest fish in the refuge are occupying the coldest part of it. Here, this is a paper by Jonathan Armstrong, where he observed that juvenile Pacific salmon were observed to switch and migrate throughout a reach of a river during the day, where they were seen to observe or exploit thermal regimes to optimize their growth and survival. The next relevant paper that I'll talk about is by Joseph Ebersole, where he had been observing rainbow trout in the Pacific Northwest of North America. And he also saw that the largest rainbow trout were also housed in the coldest part of the thermal refuge. So a lot of themes so far about big fish in cold water. This is a paper by Anton where he had seen adult salmon aggregations in the Southwest Miramichi. That study was where we got that picture from earlier. And so what he observed was adult salmon were exploiting thermal and hydraulic regimes. So the larger fish, again, were selecting for the coolest temperatures. And with this as well, he conceptualized that they were forming salmon pelletons such to reduce the hydraulic drag that the larger fish were experiencing during a behavioral thermoregulation event. The last paper I'll discuss is by Nathan Wilbur, where he was viewing brook trout and Atlantic salmon in a similar place. He was looking at it in the Cairns River, which is a part of the Miramichi River system. So what he had seen was that salmonids were seeking specific depths and thermal regimes. And on this right-hand column here, we see the largest brook trout, which were seen to occupy the deepest parts of the Cairns River that was being viewed, as well as the coldest parts of the river. So all of these papers, they look at a bunch of different physical parameters, but each of them are unified by temperature. They all look at the largest fish being found in the coldest parts of the thermal refuge. And this lays out the foundation for my study on the Little Southwest Miramichi River. So what we propose is that when we show up to it, or I guess in the morning, during a very hot day, and based on the literature as well, the first fish that will begin behaviorally thermoregulating are the largest ones. And so this is a physiology thing where the largest fish will stress out first due to temperature. So we assume that the larger fish arrive at the refuge first, followed by the next largest fish, the 2+ par, then the 1+ par and the young of the year. So this leads us to our research question, where how do salmonids distribute themselves throughout a thermal refuge? We showed up to the site and we had adult brook trout, 2+, 1+, and young of the year in the aggregation, and we want to know how they distribute themselves throughout the refuge. And so the prediction here is that the larger salmonids will occupy the coldest regions of the refuge, and this is based on the previous literature that I've spoken about. So our study area is a 1.1 hectare reach at the confluence of Otter Brook and the Little Southwest Miramichi River. Otter Brook has a topographic drainage area of 11 squared kilometers, and the Little Southwest has a topographic drainage of about 1,300 square kilometers. The historical discharge of the Little Southwest Miramichi River ranges from 6.8 to 241.3 cubic meters per second, and the average air temperature throughout the year is 4.3 degrees Celsius, with the warmest monthly mean temperature being 18.8 degrees Celsius. And this site is culturally significant. I'll point out that right here, this road is an ATV trail that will run right across the Little Southwest. So in terms of culture to the people of the Miramichi River system, this is, I guess, a relevant site to people that like four-wheeling. So for the day of study, the study happened on Friday the 13th in August of summer 2021. The air temperature reached a balmy 32.7 degrees Celsius with a discharge of 8.2 cubic meters per second. So thinking about the historical norm or the historical range of 6.2 being the lowest, this is a very low discharge period. The river temperature, the main stem maxed out that day to be 31.5 degrees Celsius. And the species present, we observed a couple of different cyprinid species, well, I guess just dace for cyprinids. And then we had brook trout and adult Atlantic salmon, or Atlantic salmon as well. So this is a historical temperature plot of the temperatures that we observed or throughout the last 29 years that were observed on the Little Southwest Miramichi River. What we see here is that the 13th of August, 2021 is one of the warmest, if not the, yeah, it is the warmest, where the main stem had hit 31.5 degrees Celsius. I'll point out that throughout these last 29 years, there have only been 9 days where the main stem has reached temperatures comparable to this. There have only been 9 where the temperature has been exactly above 30 degrees Celsius. So for data acquisition, if you know anything about Anton, he really loves drones. So we showed up to the study site and we had a drone on hand that when we observed a thermal aggregation, we were able to throw it up in the air. We call that ad hoc UAV technology because it's there for that purpose. We also use thermal infrared imagery with the thermal sensor mounted to our drone, where you get images like this. Ours are a bit more simplified, but it's basically an image that we can link to the temperature of the medium being imaged. And then we also had used visual observation with polarized sunglasses on the bank to acquire data pertaining to which fish were observed to be where throughout the thermal refuge, as I'll make clear in the coming slides. So the visual observations were jotted down on this field book here, where you can see a rough outline of the river, the tributary, and then all of the fish that were observed to occupy throughout that region. And we use polarized sunglasses because it greatly aids the ability to penetrate the surface of the water visually to see what's going on there for relative fish abundance and habitat occupancy. For the thermal infrared imagery, I'll confess that it doesn't actually measure temperature directly. It measures emissivity, which is the amount of light that's being reflected from the water. So for example, thermal infrared imagery isn't perfect. If you put a coffee cup in front of a mirror and then looked at the mirror with a thermal camera, you would see that the mirror is the same temperature as the coffee cup, which you would know to not be true. So it's just looking at the thermal infrared light that is being reflected, which is a limitation of thermal infrared technology itself. As such, we had to calibrate our thermal infrared imagery to make sure that the temperatures we were extrapolating from the thermal infrared data was accurate. So we had taken n equals 42 field points with a y-psi that had an accuracy of 0.15 degrees Celsius, or I guess an error of 1.5 degrees Celsius. And then we had also checked for differential in temperature between the surface and riverbed to see if there was any vertical thermal stratification in the river. For fish identification, I'll gloss through this very quickly because I'm sure everyone here knows what these fish look like. But that is a young of the year 1+ and 2+ Atlantic salmon par. It's relevant to discuss the size differentiation between these different age classes as we used visual observations to differentiate between them from the bank. And that's from David Roth's unpublished data. He was very grateful or very gracious to give me those pictures for this project. So for the workflow of the project itself, we had first taken a red, green, blue site map of the Otterbrook and Little Southwest Reach that we had been looking at for our study. And then we had basically made an outline of the river that we filled in with a 1x1 meter grid, filling out the entire reach. And then what we had done was based on the physical observations that were made, we filled in GIS a relative amount of data points. So basically what we did was we made a grid, and then within the grid, thanks for bearing with me, we put in data points of what fish was observed to be there. And I will explain a little bit more clearly in the next slide what we did specifically with that. But once we had all of our data input, what we did was we extracted, all of the temperature data for each respective point so that it gave us a data set of the temperatures that each age class and species was observed to occupy. And so what I meant by putting those points in, this is a much better visual, was we had a grid and we wanted to limit the amount of fish that we could put in each grid to 5. The number of fish that were seen in the thermal refuge were way too numerous to count. So we needed to go off of relative abundance and try to be as quantitative as possible with our qualitative observations. So we filled them out as such, where we had our age classes and species represented by a different color. And then we did this throughout the entire grid based on the visual observations that were taken at the time. So these are semi-quantitative points, and they are meant to represent a relative density of fish. They're definitely not perfect representations, but they are meant to just represent what we had seen on the day of the study. So for the results, we calibrated our thermal infrared imagery, no problem. And there is evident thermal stratification in the thermal image as observed. We were also able to analyze the distribution of fish based on this. And this is the first picture where we can really see the aerial extent of the thermal refuge and I guess the full size of it. So from the confluence of the tributary to the end where we saw the young of the year to taper off, it's about 110 meters of thermal refuge. So you think about this whole region being chock full of fish, 110 meters, 120 meters, you get quite a few fish, and it's obviously way too numerous to count. So for statistical results, just to throw this in there, we do have statistically significant data where we saw that the average temperature each age class was observed to occupy was significantly different from the others. This is a bit more meaningful of a table where we see the average temperatures that each age class was observed to occupy. And an interesting thing to point out here was that from our data input, what we see is a 5-degree differential between the 2+ salmon par to the young of the year. So across juvenile Atlantic salmon's age classes, we see a 5-degree differential in the preferred temperature throughout the thermal refuge. This also really helps visualize the statistics a little bit better. We have a box plot where the boxes represent the upper and lower quartiles of the data, with some outliers visualized in the young of the year guild as well. And it's important to note that none of the boxes overlap, which means that they're all statistically significantly different. Now I'll talk about the thermal variability that we observed throughout the refuge. So we did 4 analyses of the thermal refuge in terms of the thermal variability. This is the first where we had taken a longitudinal cut through the thermal refuge and had gotten this sort of thermal profile where it dips right away and then it's seen to asymptotically increase with the main stem until there's a small differential maintained. We'd also performed 3 cross sections throughout the thermal refuge. So we had taken our first one at 7.5 meters from the confluence of the tributary and the main stem. And what we observe here is mainly 1+ and 2+ salmon par present at this location. And what I'll point out here is the extreme temperature differential that you observe as you go from the bank to the center of the refuge back into the main stem. So you go from 26 degrees down to 22 degrees over about 2 meters. And then as you increase towards, or keep going away from the bank towards the main stem, you see an increase of about 8 degrees Celsius over another 2 meters, which is an extreme rate of thermal mixing when you think about how short of a distance you're going through that temperature differential. Next, I'll talk about the thermal variability at the second cross section. Here we observe that there was mainly 1+ in young of the year at the cross section. And you see the same sort of nature in the thermal trough where you have a decrease as you first go from the bank to the center of the refuge, and then continue towards the main stem. You see the heating of the refuge once more with mixing with the main stem. Next, we took a cross section at 120 meters at the very tail end of the refuge. And at this point, what you observe is just young of the year. And at this point, the main stem and the thermal refuge are different by about 1/2 degree. But what's really important to keep in mind here is that this temperature differential is still significant enough for the young of the year to want to, or I guess to aggregate here and have a stable thermal differential from the main stem that is suitable to behaviorally thermoregulate at. So looking at this all together, I'll talk about the backdrops and the color now. So we filled it in where we basically had the most abundant fish at that region. So here we have 2+ most abundant at the 7.5 meter cross section from the confluence of the tributary. And then on the edge of the refuge, we see the 1+ fish are on the outskirts of the refuge. Same thing goes here, except with younger age classes. We have 1+ fish in the central part of the refuge, and then on the outskirts, we see young of the year. And then, of course, we see this very small temperature differential maintained between the main stem and the refuge. Now I'll talk about this contour plot, which I think visualizes the busiest part of our thermal refuge. Here we have a contour line placed at every 0.5 degrees Celsius differential in the main stem. And so what we see here are 3 big things that I'd like to talk about for observations that we made. First off, we have no fish in this region that is very thermally stable, which is very puzzling to us, and it's something that we can talk about later. We also see the thermal mixing with the densification of lines about the thermal refuge, and we can talk about how that's being used by salmonids in our observations in this study. And then there's also young of the year outliers pictured here, which I will also talk about. So with the mixing at the periphery, what we see is that extreme rate of thermal mixing at the edge of the refuge. And that's sort of an opportunistic place for younger age classes to occupy the edge of the refuge, which is colder than the areas that are being maintained by the older fish. And that's really highlighted in this video here from an underwater camera at the site. There's 2 main things to point out here. So first and foremost is that this right here marks the edge of the refuge. Right here, the water is very, very warm as these fish are aggregating right here. So it marks the edge of the refuge. And then what we also see in here is that there's stratification between the age classes. So we see 2+ salmon par here on the outskirts, and then we see a larger brook trout towards the center of the refuge where it would be a colder pocket. And so this slide accentuates that even further, where you see that since you have this rate of thermal mixing towards the outside of the thermal refuge, it's not thermally stable. However, this temperature is a little bit colder than what the rest of the young of the year are holding at in the back. So because these fish are able to withstand behavioral thermoregulation at 30 degrees Celsius, it's excellent that they have that temperature there. And this outskirt right here of the thermal refuge is less stable. However, it won't exceed the 30 degrees Celsius. So if they can hold out a bit colder of a temperature, the 1+ fish won't want to be there, but the young of the year can occupy that comfortably. And because it's colder, they will select for it. Now we'll talk about the young of the year outliers that we observed in our box plot on the bottom right-hand corner here. So we observed that brook trout and young of the year are seen to occupy at very similar temperatures, about 22 degrees Celsius, give or take. And so what we propose here and what we know about this part of the thermal refuge is that this water is very shallow. So it would be unsuitable for a larger fish to occupy due to things such as predation, where they'd be more visible to predators that are lurking in that region, as well as the fact that larger fish would not be suitable or well suited to occupy here as it is too shallow for them. Like it was very shallow in the range of centimeters. I'll talk about other young of the year outlier points. These are the ones that are just below the box here. And these are marked by the young of the year that are occupying the edge of the refuge where there's high rates of thermal mixing. So as I said again, this is a thermally unstable region of the thermal refuge, and the young of the year are able to select for this temperature because it may fluctuate to be a bit warmer than what the 1+ par can withstand. However, because they can aggregate at this 30-degree temperature, they can also aggregate here where there's less stable temperatures. However, it is colder at times. And again, this chart does accentuate that very well. Now I'll talk about habitat vacancies. So we don't know for sure that this region was vacant. And that's because at this region, there was a lot of broken water. Because we weren't able to snorkel this, we don't know for sure that there weren't fish nesting in the gravels below the turbulence. However, this broken water shows that this would be an energetically unfavorable place for a large brook trout to hold at, for example. However, we feel it's not our job to say that there weren't young of the year fish here because they could have easily been nested in the gravels and we weren't able to see it due to visibility. So now we'll talk about the limitations of our study, as it's very important to do so. We weren't able to identify fish by the drone. So obviously that leads our data to be very subjective, where we had a visual observer on the shore just looking in at the river, and then anyone could do that and then take different data than another person doing it. Important to consider here is that we're trying to differentiate between fish that are quite small. So a young of the year, 1+ and 2+ are very similar in size. So the refraction that occurs with visual observation, as well as working in 3-dimensional space with fish stacked on top of one another, makes it kind of difficult to quantify the fish density. And it also makes the fish appear to be different sizes than they may truly be due to light refraction. And again, it'd be very difficult to differentiate between 1+ and 2+ fish. And we have those subjective observations, as I've said, that are imposed on very high precision thermal infrared imagery. So there's a mismatch between the ability to look at fish with the human eye and then look at fish and temperatures with a drone that measures very precisely. So this study highlights a disconnect between thermal infrared technology and visual observations. And so we were able to validate our prediction. We explained the outliers that were seen in this study. And these studies are obviously very important in a changing climate to understand how salmonids will withstand a continuously changing climate. With future research, we'd hope to be able to quantify fish with the drone to take out the subjectivity of human error in this study. And I'd also like to acknowledge my funders, the WTF Trust Fund. Yeah.